So we will move on to doing so up until now we have done streaming algorithm for several problems, and lastly we were looking at streaming algorithms for matching. Okay, so what we saw that on graphs of bounded arboricity, right? What did we saw? We saw two results here. We saw on graph of bounded arboricity, we can estimate the matching size. We can estimate the matching size in some f of epsilon times log n, I think, or poly log n. I don't remember very well. I think it was log n. We had some log n string, or I don't remember. Estimate the matching size to something of this nature, like estimate the matching size approximately, okay, in this much time, in this much space. Okay, we also saw 2 plus epsilon approximation for matching on weighted graphs, okay, with space some n poly log n, right, and that was based on our local ratio algorithm. Okay, but a natural question at this point of time will be is that fine but this is like an algorithm which were allowed to just look at the stream just once, but what happens if we allow multiple passage on the stream, like streams are coming, so believe that these streams will cut down and it will come again, okay. So number of times the stream comes, so suppose number of times stream comes is p, then we call it p pass algorithm, okay. So a very natural set of question is here that I agree that 2 plus epsilon approximation for matching on weighted graph we can do in n poly log n space, but matching is a polynomial time problem, right? We can solve the matching in polynomial time, right? Is it possible for us to do matching better than 2 but in multiple passes? Okay, right? What can we say if we take p passes? Okay, so these are the natural question to hold, and there are results which shows that we can actually, for matching, we can come up with 1 plus epsilon approximation in some of epsilon, some other maybe log n or something passes, okay. Okay, so this is the current known, the best set of results, but to get there we will forget all these things and learn entirely new methods of doing certain kind of updates and things, and get back to this once we have understood this method concretely. N poly log n, poly log n epsilon or something like that. Poly log n, yeah, and some f of r. Epsilon is not very bad actually, it's like epsilon square minus 2 or something. So we'll get there. I mean, I don't remember this result very well enough to. Okay, so that's a goal, but the way we learn some new tricks here to do this, we'll just forget the streaming algorithms and everything, and we'll learn a method called, we'll see, okay. Yeah. So imagine yourself okay. So imagine that you are interested in some stock. So there could be many, but let's say we are interested in some particular stock. particular stock, okay. And every day he wants to predict whether the price of the stock is going up or going down. So what is the prediction? Price of stock is going up or down, right? So this is what you just want to predict over a period of time, okay. But now this is a very difficult question because stock market could be very vulnerable, adversarial and everything, right? And you are a just common person. So what I give you is some N experts which advise every day you look and then you can make your prediction, okay. And at the end, you know, and say at 5 p.m. what happened, okay, or once you have made your decision, I will show you whether stock has gone up or stock has gone down, okay. So you have an access to N experts, okay. You have an access to N experts, okay, and you can okay, you have an access to N experts, and what you could do is that follow your expert, right? You decide to choose an expert and follow his advice, okay. Decide to choose an expert and follow his advice. What is the most natural way of doing this? What should I do? I mean, I can look at N people, and so what should I do? I mean, right? I could do majority, right? If majority of these people are telling me that it is going up, then I decide to take it up. If majority of them are saying down, then I decide to go down. And if both of decisions are equal from these experts, I just choose one of them arbitrarily. Okay? Okay. Okay. So I could do majority. Vote over experts. Okay. So what will be this algorithm? So okay, but notice what could happen, that my experts are making wrong decisions. Like maybe I realize that after 5, 10, like after say looking at them for 5 rounds, 6 rounds, that this majority decision following is just bad. I mean, like every time they are making wrong decision compared to me, right? So what happens if you make correct decision, you get nothing. You make wrong decision, you lose $1. Lose, right? So you don't gain anything, but you lose. If you are not making the correct decision, you lose $1. Okay, so this is the cost. This is the cost of your decision. So if you made a decision, either the cost is 0 or cost could be 1. Cost is 0 if your decision is same as whatever happened in the market, but if your decision is opposite to the decision of what happened in the market, then I pay $1. Okay, so this is cost of our decision. Okay, now if you look at this, right, as I told you, right, maybe majority rule is rule I am following now for some number of days, and I realize that hey, these guys are making too much of mistakes, right? So at this point of time, either I can just follow this rule or try to amend some things, right? So what did our machine learning told us? That we learn from our experience, okay, right? So we learn from our experience.
Unknown caller.
It never rings, and when it shouldn't ring, it rings. See, it's a random variable. Okay, so we should learn from our experience. And what do we mean by learn from our experience? Those guys who are making consistently wrong decisions, like those experts whose decision is consistently wrong, I mean, we should just like somehow we should start giving them lesser and lesser weight. Like we should like maybe in the beginning we do not have much knowledge about each of them, but as we go further, we have more and more information about these experts, right? And we should start saying, oh, this guy is a better expert, this guy is a lesser expert, and we should somehow weigh them according to their expertise or according to the amount of truth they have told up until now. Right? We all make this, right? I mean, when you go to a doctor in the beginning, you don't know how good, bad a doctor is, right? But after 2-3 times, you know how bad or good doctor it is. If it is a good doctor, you persist with him. If it is a bad doctor, you try to search for another doctor, right? So this is a very natural tendency. So you can try to model leaving someone or not leaving someone if by giving them some weight and choosing someone proportional to its weight, okay? So this is where this algorithm is called weighted majority algorithm, okay? Okay? So this weighted algorithm tries to make this trivial algorithm correct, okay? This trivial algorithm like which takes weighted majority, it tries to correct this error or corrects this, like I'm making consistent mistake all the time, it tries to correct these kind of errors, okay? Okay, so rather than predicting, you know what I do, rather than predicting up or down based on majority, I will make a decision up and down based on weighted majority, right? So I look at up and I look at who all have said up, I add their weights. Down, who all has said down, whichever value is larger, I just go with that decision, right? So this is like a weighted majority. So that gives us an algorithm what is called weighted majority algorithm. Okay, so what is weighted majority algorithm? Okay, okay, so in the beginning I don't know who is good, who is bad, right? So I initialize in the beginning, okay, so what I do, so I initialize something, okay, in the beginning I don't know anything, so I first fix an eta which is less than equal to half, okay, and with each expert I, okay, associate the weight Wi1 equal to 1. So this is my initialize. In the beginning I give them all of them equal weighted because I have no idea how good, bad they are. Now for t equal to 1 to t, what I do, make the prediction, okay, that is a weighted majority of the experts prediction. Okay, so it's like W1T, W2T, right? So this is my, in the Tth round I have some weight and I look at those weights and based on that I make the prediction. So what do you mean? That is predict up or down, okay, depending on which prediction has a higher total weight. Okay, higher total weight of experts advising it. Breaking ties arbitrarily. Okay, so this is what we do. Okay, now what I do in this, all those experts who has given me wrong advice, I decrease their weight. Okay, this is what I will do. Okay, for every expert I who predicts wrongly, okay, decrease the weight for the next round okay, by multiplying it by a factor 1 minus rho, okay, 1 minus eta. So what is this? Weight of I in t plus 1th round is what? 1 minus eta, okay. So this is your update rule. So this is my algorithm. This is what I do for this. And what is my goal? I want to, so if you look at, remember our machine learning algorithms, then in such scenario you cannot do too good. So what we would like to do, we would like to do as good as these experts, right? So we would like to do as good as the best expert, right? Meaning algorithm should make not more mistakes than an expert makes, than the best experts makes, right? You understand? So I do not want my algorithm to make more mistake than the best expert makes a mistake, right? I mean that's the best I can hope for. Okay. So in other way, what do we would like to prove? Okay. So this is my algorithm. So for correctness, what I would like to prove is that so if I prove that with respect to any expert, I am not making too many mistakes, like I am upper bounded, like number of mistakes I make is upper bounded by the some constant or something times the number of mistakes made by that guy's expert, it also implies that I am making not too many mistakes with respect to the best guy. Look, if I can bound with respect to the best guy, I can of course bound it with respect to any guy, because other guys are only going to take more mistakes. Okay, so this is what we are going to do. So what I am going to prove to you is the following theorem. After t steps, okay, after t steps, let MIT be the number of mistakes, of expert I, okay. This is what the number of mistakes an expert I makes. and MT be the number of mistakes, the algorithm makes. Okay? Then for every I, we have the following bound. What is this? M of t is less than equal to, okay, 2 times 1 plus eta times number of mistakes made by this expert plus 2 ln n by eta. Okay. So, in particular, this holds for the best expert I, holds for I which is the best expert, or who is the best expert, okay, that is having the least MIT value. Agreed? So, this is what I like to show, right. So, if I show this happens, then I have shown to you in certain sense that I am not making too much mistakes compared to, right, like some constant times something, okay, because for fixed eta this is like a constant like order 1, and this is like, say for example eta equal to say 10 if I put, no, eta equal to I put say 1 over 10, right, then as I go closer to 2 if you notice, right, this starts to grow and we get closer to this, okay. Anyway, so how do we go about proving this, okay. If you apply some simple induction on what is that called, on I, then we can see that W weight of, sorry, induction on T, okay. So what we will be able to show, if you see correctly, is weight of I in T plus 1th round is equal to 1 minus eta times weight of, okay, no, okay, times, so this is my expert I, okay. So Mi of T, okay. So what is the weight? Look, after each round, if you notice here, what do? If you have made a mistake, then I multiply your weight with 1 minus eta. So in the beginning I start with 1, right. So as many times I make a mistake up to t times, I multiply with 1 minus eta, 1 minus eta, 1 minus eta, 1 minus eta. So 1 minus eta into Mi times t. So this is by induction on T, you can prove this. No? Huh? What? Multiplied by Wi. Why? Wi1 is 1. So I started with 1 here and I am going on multiplying this with this. Look, if MIT is 0, right, then this is 1 anyway. So this will not harm anything. If you made no mistake at all, then your weight remains 1. This is also captured by this, so I do not have to worry about those things. Okay. Now, so I will tell you what do these things actually mean later, but now let's just do the math computation. So now I am going to define a potential, okay. So what is my potential is like sum of the weights, okay. So my potential is basically sum of the weights. So I will write down what is phi of t is summation over I, okay, and weight of I in the tth round. So this is the potential function. Okay. Notice that in the beginning this potential is exactly equal to n, right? So phi of 1 is equal to n as number of experts. Each time you make a mistake, what happens? Each time we make a mistake on this algorithm, I claim that weighted majority of this, like whatever the value of this weighted majority of those guys should also decrease by 1 minus eta, right? Because look what I did, I sum these people up, I sum the weights, that whatever that weight was, sum the weights, look at the total weight, whatever total weight is, right? Sum summation star total weight, it's a V, right? How do you decide to do an algorithm? You say, hey, let's look at up, what is the value? Look at down, what is the value? Whichever is larger value, it means up or down, right, is at least going to be z over 2. Otherwise, right, because this is what you are doing, right, you are summing the weights for up, summing the weights for the down, whichever value is larger, you are going with that decision, right. So what happens if you made a mistake? It means all these people actually made a mistake, right. So basically your weighted sum drops, but at least half of the weighted sum drops by 1 minus eta, right. This is correct. So what is the change in potential in IF plus 1th round? Look, either I do not make a mistake in this round, look, so look at how phi changes, okay. 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 So suppose I have phi of phi t. Okay. No mistake means what happens? If I make no mistake, then also phi could change actually. But it could be negligible. I don't know. Right? No mistake also, I mean, phi t plus 1, I mean, I don't know, maybe all of them were making a correct decision. So phi of t plus 1 could be equal to phi of t. Could be. Okay? Could be. I don't know. But look at the case when phi of t, what happens? When makes a mistake. When you make a mistake, it means in the next time for lots of half the weights sum, you are going to multiply with 1 minus eta, 1 minus eta, 1 minus eta, 1, half the weight. Maybe the number of people who contribute this half is 1 minus eta, like 2-3 people, but their weight was larger than this. To that weight, you are going to multiply with 1 minus eta, 1 minus eta, 1 minus eta. Right? So, what is phi of t plus 1 in this case? Yeah. So, in this case, phi of t plus 1 is less than equal to phi of t times half. I may not have done anything to that half, and for the remaining half, I have decreased their weight by 1 minus eta. This is it. Okay? Agreed? Which is equal to phi of t times 1 minus eta. Am I right? Half plus, sorry, eta by 2. Agreed? Correct? Okay. If we apply induction on t, what can we show? Phi t plus 1 is equal to 1 minus eta by less than equal to 1 minus eta times m, what did I define? M of t times n. A small n. Look, what is phi of 1 is n, right? You drop only when the algorithm makes a mistake. And what is m of t? Number of times the algorithm makes mistake. This is it, right? So each time algorithm makes a mistake, I incur, like, the cost drops by 1 minus eta by 2. Okay. Notice that phi t plus 1 is greater than or equal to beta of I t plus 1 for all I, right? Because this is a positive quantity, right? This is a positive quantity and this is sum of all these beta. So at least they are greater than their individual quantity for sure, right? So now we are ready to get this proof, okay, right? So now let's look what we know about it, okay. So what is this for all I, right? We proved this is equal to this number, am I right? Right? So if you notice here, what did we get here? We get here that phi of t plus 1 is less than or equal to 1 minus eta by 2 to the power m of t times n, which is less than or equal to, like, for a fixed I, right? This is true about any I, right? Not fixed I, for any I. What do we have? This quantity is less than or equal to wi t plus 1, which is equal to, because of this condition, 1 minus eta times to the power mi of t. This should be here. Do you agree? Right? This is what it is. So now we have got, so now I will equate this and this and get the desired bound. Okay. So take log both sides or ln both sides. So what you will get? You will get mi of t ln 1 minus eta is less than or equal to ln n plus, why am I writing m of t, right? M of t, right? Ln n plus m of t ln 1 minus eta by 2. Agreed? Okay. So let's multiply with minus 1 both sides so that this inequality becomes this, right? So minus this is greater than or equal to minus minus. Agreed? Okay. Now I look at this quantity, and I can approximate with, if you write Taylor expansion or something, it is equal to eta, like eta plus eta square by 2 plus eta cube by 3, a 3 factor, something like that. I don't know. I think it's 3 factorial. No. This is why it's alternate with respect to the, look, if because of this, no, if it is plus, it is alternating. Because it is minus, everything is minus, and then if it minus, everything will become plus. Yes. What? Okay. Now, since eta is less than or equal to half, all these quantities can be upper bounded by just another half, right? So I can replace this, replace minus ln 1 minus eta. I mean, of course this is less than this, but I am going to replace that all this quantity, I am going to replace that not only this is larger than this, because I will replace something larger by, because if I take eta square common from here, you will get half plus 1 by 3 factorial blah blah, that is less than 1. Okay. So what you will get here is MIT eta plus eta square is greater than or equal to minus ln n minus this. Now you take minus here, right? Everything is positive here. Every quantity is positive here, right? So it is at least greater than or equal to just eta by 2, right? So this is equal to minus ln n plus m of t times eta over 2. First term of this expression. Where? Here is ln n minus ln n, which is there. Okay? But now you take it other side, right? What you get? You get m of t is less than or equal to eta plus eta square times 2, because 2 goes there, plus ln n divided by plus 2 ln n divided by eta. Right, I am missing, what am I missing? Mi of t plus 2 times ln n. Okay. Now if you, which is equal to, if, right, here if I take all this, then it will become 2 times 1 plus eta mi of t plus 2 ln n, ln not n, right? Yeah, it is ln n, right?
Okay, that's what my question was. Is that ln n or ln theta?
It should be ln n, no? It should be ln n.
This equation it is ln n.
Yeah, it should be ln n. My mistake. Eta. That's it. So this is what we wanted to prove. Okay? So the proof is fine, right? So I'm not making too much mistakes by this weighted majority algorithm than this. But notice one more thing is that this is a deterministic algorithm. There is no randomization, nothing involved here, right? But suppose I want to get rid of this 2. I want to get rid of this 2 because like this 2, if you do deterministic algorithm, there is no way you can. But what you could do probably for randomized algorithm is that I look at these weights and think of these weights in some sense as probability distribution, and it's like a randomized rounding. Okay, so I pick a decision with probability proportional to the weight, right? Okay, so if the weights are like 3/4, then I go with up with probability 3/4 and down with probability 1/4, right? I choose up with probability 3/4 and down with probability 1/4. So every time, rather than so this is also called, notice, yeah, this is like weighted majority algorithm, but notice that you are multiplying some quantity to the weight, and this is why it is also called multiplicative weight update. Okay, and we did this kind of thing also when we were trying to do in ML course. Also we did some of these kind of things. It actually comes, so these algorithms actually come from ML, and basically some of this comes from game theory, but you can also apply into lots of other settings. Okay, so now what is our next goal is to somehow get rid of this 2 with the help of randomized algorithm, and what you like to do is that think of these weights as probabilities. And how can you think of these weights as a probability? That's very easy, right? You look at each guy's weight and divide by the sum of the weights. It automatically gives you a probability distribution on the set of elements, set of experts, right? So now I would like to choose, so up until now we are looking at weighted majority, but now in my randomized algorithm my job will be, okay, I want to choose an expert and I want to go with his opinion, which is same as choosing that expert with his, like, with proportional to the probability associated with that expert. And how do you associate probability? Oh, whatever the weights you have, that weight divided by the sum, right? That automatically gives you a probability distribution over experts. right? I will like, and now let's see what happens when we do these kind of computations, okay? So now we will move away from this algorithm. So let's look at the beauty of this algorithm first of all. It doesn't depends on whether these experts are correlated or not correlated, right? They did talk to each other or not talk to each other, right? It also doesn't assumes in which sequence the events happen, right? Nothing, right? What is the current weighing of the expert? It assumes nothing about weighing, experts are correlated, how events are happening and all these things. So what we will see next is an obvious generalization of this, and this is also a reason why it gives rise to diverse applications in different algorithmic fields. In particular, imagine the scenario where these events are chosen adversarially. It should resemble what is called zero-sum game in game theory, okay? So you can prove lots of good properties about zero-sum game theory by the next obvious generalization which I am going to give you, okay? Okay. Okay, so in most general setting, okay, so we'll update this algorithm. Okay, let's remove the proof. Okay, we might be able to salvage some aspects of statements which I have written here. So now we have, look, first of all, I gave you a very simple experiment here. It was a binary decisions, right? Binary, which is not the case always. So we will still assume that we have n experts, okay, but we are not going to do some binary decision. What will be assumed that to model that you could have many more outcomes than just binary, what we will we'll just get rid of all these predictions and all this altogether, and what we'll say that in each round, so what we'll do in each round, every expert recommends a set of actions, okay? Okay, every expert set of, right? And if we choose a particular expert, what are we going to do? We are going to implement the set of actions told by this recommender to us. Am I right? Did you get the setting? We still have n experts, we will have several rounds, but now rounds, like we were making a decision, oh, we'll go up or down like stock market. So we can think of that like a binary decision, but we might have many more decisions than just one or two decisions, right? So now in every round, expert will tell, oh, do this or do that, but the number of actions it could take is many, right? The set of decisions, set of choices which could have is way more than just two. But if I choose an expert I, then I just follow his advice, okay? Okay, and what is our task? Our task is to pick up an expert and follow his advice. Follow his advice. Okay. Once I have followed his advice, then I see the cost vector. Okay. You do not see, like, so for example, what was the cost we paid, right? So we said if you made a mistake, the cost we paid was like $1. Like if the stock market on that day was like up and I chose down, then I paid $1, right? So once I have performed this task, cost vector is revealed, okay? So how will we model this? Right? Do you understand? What is a cost vector? It will be like an n length vector. It's like, oh, you followed him, then you have to pay this much of cost, right? Because I could have thought of our cost vector in this setting, n expert is like, think of this cost vector, expert 1, expert 2, expert n, right? If I choose up, right, and expert 1 also told us to choose up, then the cost is 0. But expert 2 told us down, right, and I chose an action. So this is it, you first action happens, right, first action happens, then the cost happens, right, because different action could lead to different costs, right. If you chose up, then all the people who told you to do up, they may not have to pay any cost, right, but the people who told down, they have to pay, right. So this is how the cost vectors, like maybe 0, 1 and something. So after I have made an action, followed some expert advice, I say, hey, here's the cost vector. If you have followed this guy, then you have paid this cost. If you have followed this guy, you will have to pay this cost. So this is the cost vector which comes into play, right. So this is the setting where we're trying to work on, okay. Okay, so what is the best way to choose an expert in the beginning? I have no knowledge about expert. What do you do? Huh? You randomly, uniformly at random select an expert. Great idea. And what does it mitigate? It's like, okay, it's like, in some sense, these weight vectors, I should think of this as a, so what you did, you selected uniformly at random one of the expert's opinion, one of the expert, and you followed his opinion. This is what you did, like in the beginning. But as you learn more and more, you should start, so what is this meaning that I chose uniformly random? Everybody I gave a weight probability distribution 1 over n, 1 over n, 1 over n, 1 over n. But as I go further and I learn more and more, I change my probability distributions accordingly, right, which it basically means I am changing the weights associated to these experts accordingly. But rather than choosing them deterministically, now I choose uniformly at random, not, I think uniformly at random is the wrong word, I chose uniformly with respect to the given probability distribution. Okay, so you understand the goal of this. So when you pick an expert uniformly at random, what happens? What is an expected cost? What will be expected cost? If you picked some expert uniformly at random in the beginning, what is an expected cost? Average cost. No. No. What's my random variable? I could choose any of these guys.
Number of experts saying yes, but
No, there is no more yes and no. Everybody has a cost associated, right? I made a decision, so I'm going to choose him. So expected amount of cost is going to be summation over, look, for I guy, right, for choosing this I is expected cost I sum mi, like whatever you, once you chose I, you have a cost vector revealed, right? So this into the corresponding probability, right? So that is the expected cost, which is like an average. In the beginning, it's like an average.
Cost depends on the action or on the expert you choose.
What?
The cost depends on the action.
Look, the moment I choose an expert, action is fixed.
But if I choose the same action, are you choosing different experts?
I'm not choosing an action, I'm choosing an expert. I'm choosing an expert that, so in every round I choose an expert, and what is this? Look, in each round every expert recommend a set of action. It's fixed. If you choose him, this is what he's going to tell you to do. Okay? Now, if I chose him, then I know what to do. But if I did this, then my cost is this much. Right? So now if I'm asking you, what is an expected cost? Okay. What is an expected cost if I chose I? Then it is cost vector times probability distribution. That's it. I'll make them much more cleaner as I go. Right? Okay. But you understand my point. Look, what happens? So I chose my expert with some probability distribution. So suppose I chose him, then a particular cost vector appears. Right? A particular cost vector will appear. And then what is my expected cost? My expected cost is, look, if you chose him, but look at the probability of I of him, right? Or think of this. What did you do? You chose him then into this cost, plus you did not choose other guys into their cost. So what is the probability of not choosing other guys? 1 minus this, which is same thing as you sum over them and multiply their cost. It's a weighted average. Right? So think of this way. So I chose I, then cost is say C1, C2, Cn. If I did this, then this. And suppose I have a probability P1, P2, Pn. I chose Pi, then I get this. Right? So what is this? Pi times Ci. But I could have chosen any of these guys, right? So that is, look, and what is the other cost? Is 1 minus Pi times summation not equal to I. J not equal to I Ci, which is same as summation Pi Ci. That's it. I going from 1 to n. That's it. This is what all that is happening. What is an expected cost? Okay. Chosen, I chose means I did not choose other guys. So what is my expectation? Expectation is, what is my expectation? Expectation is like cost is expected, right? This is fixed, but what is my expected cost? Expected cost, like if I chose this, then I know I took this, right? But what is the probability of choosing him is Pi. But I could have also not chosen some other guys. So you have to multiply with them. No? Okay. Okay. So as the events happens, you will start noticing that some experts are much better than others. So how do you reward them? By increasing their probability of being selected, right? And this is what we are doing here by increasing their weight, or rather decreasing other people's weight. Okay? Okay. You know what is Shannon entropy is? Okay. So Shannon entropy, the best way to think of this is that is a measure of the average information content one is missing when one does not know the value of the random variable. For me, what is the cost? It is a random variable. Based on what do I choose, I get, like, look, based on which expert I choose, I get different costs, right? I get different cost vectors, which, because, right? So this is like a random variable. For each round, expected cost is like a random variable, right? Which we do not know, right? So when you choose uniformly 1 by n, it shows you that you have absolutely no knowledge about anything about this random variable. right? It shows our complete ignorance. But as we grow more and more, what are we doing? We are trying to decrease this entropy or this information content, like, because now we are more and more knowledgeable. So one way to look at this algorithm, this multiplicative weight algorithm, is that there is some like we quantify the not information which we have, like the information which we do not have, and every step we are trying to decrease that quantity. Okay, so if you know a little bit of information theory and all this, so this is exactly what this algorithm is trying to do and achieve. Okay. Okay. So as we learn about them, we skew the distribution, right? We skew more towards this, and this shows, so I'm reducing the information content about the random variables, right? Because now there's more likely that you are going to choose one with a higher probability, right? So you are, from the system of experts, you are reducing the content, like reducing the no information content as much as possible. Like, for example, if I would have just put 1 at 1 and everybody 0, then I know this is the best guy, let's just go ahead and do something from him. Okay. Anyway, so those were like some jargon. So now let's set up, so this is called multiplicative weight algorithm. Okay. So what we are going to do, we are going to do what is called multiplicative weight algorithm. Okay. Okay, so let's set up some notations first. Okay, so these are my time steps, current round, and let I be a generic expert. Okay, I is some generic expert. Okay, in each round T, okay, we select a distribution PT over the experts. Okay, I'll tell you how to select this. Okay, and select an expert randomly from it. Right? This is what I have been telling you from this side. Say select an expert I randomly from it. Okay? So at this point, what happens? Cost of each cost vector is revealed to you. Okay?
When is cost vector revealed? After this step?
After this step. Once you have chosen this, then your what?
That you don't know.
No, you don't know. Because look, what decision you make will decide the cost vector, no? So the cost vector is not prefixed something, right? Cost vector depends on what course of action you chose, right? So it cannot be pre-decided. Cost is a function of what decisions you have made. Okay? So at this point, cost of all the actions recommended by the experts by the experts, okay, are revealed. In the form of a vector, say empty, okay, such that expert I incurs MIT, incurs cost MIT, okay. Okay, so this is one assumption which we will make, and this is a important assumptions to make, and you will see why. So they lie between -1 to 1. So cost is between -1 to 1. Okay. So this is the only assumption we are going to make, that cost vectors lies between -1 to 1, nothing more. Okay. I mean, you can choose cost vectors even if you know all the. So now, what is an expected cost to the algorithm for choosing, right? So what is an expected cost of the algorithm So expected cost of the algorithm, okay, expected cost of the algorithm for sampling an expert I. From the distribution PT is, what is this?
Summation PI MIT.
Hmm?
Summation PI MIT.
Or yeah, right. So this is going to be expectation I in PT MIT is equal to that's it, dot product, right. Is this okay? Why? So the expected cost of the algorithm for selecting an expert I from this distribution is, look, he picks him with this probability, right. So if I had to set up this as a random variable, what is a random variable here? Think about it, like here basically says that we are going to select I in P of t. Okay, so this is for you to figure this out. So the total expected cost over all rounds is therefore how much? Summation over, right, t going from 1 to t mt times pt, right. This is a expected total expected cost over all rounds, okay. This is, just sum them up, total expected cost over all rounds. And so this is the total cost we did, right? But what we would like that this total cost which we have incurred is not much more than the total cost of the best guy, the best expert, right? Which is like, so in hindsight, I want to compare this with what? Minimum over I summation mi t going from 1 to t, right? This is what I want to compare with. Even if I choose the best expert, I will definitely look, you have to understand that you are not choosing the different, like, look, I chose an expert. So algorithm might be choosing different set of experts in the algorithm, right? But we are competing with respect to what, oh, this, if someone would have chosen this expert, this much cost he will incur. If someone would have chosen this expert, he would have chosen this, and I want to just be as good as any expert there, not as good as a subset of expert there. And this is an important point to make difference between. If you remember our machine learning algorithm, what were we saying? If in agnostic park, look, hey, I do not know how to do as good, but I want to output a function which is as good as one of these functions, and each of these functions were like an expert, right? So if I chose an expert I, then I will incur this much of a cost. I want to do just as good as this, because this is what, if you notice, this is what I was proving the theorem here, right? Right? In particular for I, who is the best expert, having the least value of this, right? So this is what I want to do. I want to do as good as the best expert, not a linear combination of these experts, right? Then I cannot beat them, right? So this is what I did in the static case, and this is what I also want to do in this so-called dynamic case. Okay? Is the idea clear? Okay, so I will just do this, associate the weight vector this. Okay, what I do here, I will not do this. I will just change this step. Okay, what is this? Choose expert I, right? Choose expert I with probability proportional to its weight. Okay? Why am I writing? Yeah, correct, no? WIT, right? So that is, use the distribution. I will tell you, write down the distribution. P of t is equal to W1 of t divided by, wait, Farhad, phi of t. Okay, I will tell you what it is. Dot Wn of t, phi of t, where phi of t is summation I Wi of t. This automatically makes it a probability distribution now, right? Now observe the cost empty. Observe the cost of the decision empty. Now it's time to penalize, right? Penalize the costly decisions, okay? Costly decision by updating their weight vectors. updating their weight as follows. For every expert I, what is weight of I? T plus 1? Weight of I in the Tth round 1 minus, what do you think? Hmm? One minus eta and this is where we use the fact that this is the only place where we are actually going to use the fact that MIT does not range between
Minus 1 1.
yes, because if this becomes too high cost, then this becomes negative. Then if you remember argument we were doing, oh my potential is always greater than the individual weight, right? In the previous argument what we said, the when we were doing this logarithmic scale we said individual weight is less than equal to the what you call potential. You cannot say this anymore, because if there are some negatives, they sum this to 0, potential becomes 0, but individual could be much larger than the potential.
Here, if it become minus 1, then it increases. It can increase now, right?
No, but imagine that I have 10,
Okay.
then the weight becomes negative.
No, but here also it can increase. No.
Yeah, that's fine. We will deal with positive is fine for us, right? Because sum of the weights is greater than equal to all the positive weights, right? Individual positive weight. But sum of the weights where there are some negative and there are some positive, some could be less than equal to the individual parts, right? And we use this crucially in the last proof, and that is where we are going to use this.
Previously weight always decreases. Now that is not the case.
No, weight could increase. Okay, I am following this, but there are lots of people who follow different proof strategy for these things. But okay, let me follow this because this is how I started with. Okay. So now we like to prove a theorem of this nature, whichever we proved before, that this weight functions is very good. Assume that all costs, okay, MIT, okay, is element of minus 1 comma 1, okay. Then the, let's say MWA, multiplicative weight algorithm, guarantees after T rounds for any decision for any expert I, okay, we have okay. Okay, is less than equal to I equal to 1 to T Mi of T plus eta times summation T equal to 1 to T, right. So if it is negative, then I have taken the mod plus ln n by rho. Okay.
Middle quantity is too much.
What?
The middle quantity summation T going from 1 to T of
In what sense? Far?
So you want your algorithm has a cost which is very close to what is the best expert cost.
Yes.
So with that previously like with an additive factor of log n by eta,
Yes.
and there were some 2 there.
Hmm.
Now you have eta times this.
This quantity, right? But now eta is in my hand.
Okay, but the other thing is not
Which one?
MIT.
Yeah, but that I have as it is.
Okay.
This I can control,
Okay.
right? By choosing eta appropriately, I can control this, right? And this I have as from as before. Right? So it bounds the total cost of the bad decision of any expert in terms of whatever this guys make. That's it. Right? If I did not have eta in front of this, like then you're right. But now I have a eta in front of this, which gives me a lot of power to control these things.
So you choose even that is a function of like.
I could choose, right? Right? Because we are not talking about algorithm anyway at this point of time, right? We are not talking about algorithm. We are not talking about the number of rounds that will go. Nothing of this nature, right? All we are saying that look, for any tth round, if you do, this is what happens. If you make this decision, okay. So how do we go about proving this? So it is along the lines of the previous proof which we did. Okay. So let's try to prove this. So what we did last time, we had a potential function, right? Phi t proof. Okay. So what was the potential function? Sum of the weights, right? Yeah. So this is somewhere I wrote. Yeah. Okay. Now what is phi of t plus 1? Let's see what is this, because that only told us how things are going to change or not change. So phi t plus 1 is summation going from I, weight I, t plus 1. Right? Now notice this is going to be summation I, this into this. This is equal to this by definition. So I write down this. Weight of I times minus weight of I times t eta mi by t, right? I just substituted this here and I added this, because this into 1 minus this. This is equal to this, right? So if you take out this common, you will get 1 minus whatever it is. Now what is this quantity? Right? So this is equal to summation this minus summation this, which is equal to, what is this? What is this quantity? This is phi of t. Agreed? Okay, very good. I can take out eta common from here, right? Eta is very common. Okay, but now I can also substitute weight I from this quantity. What is weight I? Is nothing but pi times pi of t times phi of t. Agreed? So this I can write down. Please tell me pi of t times phi of t.
MIT is also there.
Yeah. Agreed? Now something should be like I can take out phi of t common. Right? And what is this? It is pi of t times mi of t. But this is a dot product of pi dot mi, p of t times m of t. So this is nothing but if I take phi of t common, then I get 1 minus eta times p of t times m of t. Agreed? This is fine? And this is less than equal to phi of t times e power this quantity. See, I will tell you, e power minus eta times p of t times m of t, correct? 1 minus this is less than equal to 1 minus 1 e power minus 1, whatever it is. Agreed? So now if I apply induction on t, what will I get? By induction on t, after t plus 1 round, what will we get? Look, what will we get? We will get phi t plus 1 is less than equal to phi of 1, right, into e power minus summation, right, minus eta summation t equal to 1 to t m mt pt. Agreed? This is fine, right? I mean if I apply induction on this, this is what I will get. Each time I will get this term, right, this replaced by this next term, this replaced by this term, and then since it is e power this, I can sum them up on the top and I will get phi of 1. But what is phi of 1? Is n. So this is equal to n times e minus eta summation t equal to 1 to t m of t p of t. Okay? Okay. So this we have got an upper bound on phi. Now we need a lower bound on phi. And how are we going to get lower bound? We wanted to say that A, look at any phi of t plus 1, it is greater than or equal to the weight at that point of time. And that I can only say if all the sums are non-negative. And that is why this is guaranteed that we will never get non-negative numbers, right? Because look, if you have a positive number and since you are only allowed till minus 1, this guy can only make you at most 0, because it can make 1, right? But it can never make you non-zero, like it can never make you negative, right? And this is important to say whatever I want to say next. Now, and this is because since MIT, my God, what a name, for all I, right? What can we say? Phi t plus 1 is at least wi t plus 1. Otherwise I could not have said this. But now what is wi t plus 1? Let us try to understand what happens to wi t plus 1. Sometimes you get negative quantity to multiply, sometimes you multiply with positive quantity. Okay, so I will tell you what I mean by this.
Less than 1 bracket or not?
Wait, so this is equal to product right? I going from 1 to t, right? Sorry, not I, t going from 1 to t, 1 minus eta mi of t. Agreed? This is what happens every time, right? This is what happens, right? You take this, next time you multiply this, next time multiply this, next time multiply this. This is what exactly what is happening up to here. Okay, now some things to note. Okay, 1 minus eta to the power x, okay, is less than equal to 1 minus eta x if x is between 0 1. 1 minus eta to the power x less than equal to this if x is between 0 1, and 1 plus eta minus x is less than equal to 1 minus eta x if x is between minus 1 comma 0. So these are like known inequalities. Okay, so let's try to use these inequalities. This is fine, right? Now I am going to differentiate between them, like which terms gives us like mi is negative and which terms mi is positive, and then I will apply one of these inequalities. This is at least greater than equal to 1 minus eta times summation greater than equal to 0 mit. Okay. So by this I means for all those terms where mit is greater than equal to 0 times yeah, this is fine. Like each term you can replace it, right? Look at this. Each term based on whether this is like whether this becomes plus or this becomes negative. Look at each term here, right? If mit
It's between 0 and 1.
between 0 and 1,
Then it is a first inequality.
then I will apply the first inequality.
Okay, now what happened if
This is the first one, and second one it will become 1 plus eta, right, minus summation less than 0, strictly less than 0 mi of t, right. So each term I replace either with this term or this term, right, and then since it is the same same base, I could sum them up, same base I could sum them up. Okay, and what this summand means? Refers to round t where mi of t is greater than or equal to 0 and where mi of t is less than 0. Okay, so now we have a lower bound and we have an upper bound. So what will we do? We will try to equate this upper bound and lower bound and try to get into this form. That is our objective. So what will I do? I will take logarithmic both sides first. Okay. So if I take log both sides, what will I get? So let us say a and b. What I know is b is less than equal to a. Okay. Take ln both sides. What do we get? Let us see what do we get. Ln n minus eta times, because look, ln this will come down and ln ee is 1. Okay. So this is summation t equal to 1 to t. Please, if I make a mistake, please let me know, okay. I mean, these are not something which I am very great at, okay, is at least, okay, if I take ln here, so summation greater than equal to 0 mi of t times ln 1 minus eta, right, correct, yeah, no, right, and plus, because this is multiplication, right, so this will become minus summation less than equal to 0 mi t, my god, people will say that I am dying to go to MIT. In fact, I could just put it inside, does not matter, because it is, I can multiply this, so why, this is fine, okay. Now let us negate it the way we did. You do not like my computation, what can I do? I mean, if this require computation, then I have to do computation. I mean, not that I am very fond of this, but you get this algorithm now, okay. I know you do not understand why this algorithm we are doing, but eventually you will understand. I will give you 10 applications of this. So let us just do the dirty thing of, at least once we should learn how to do this kind of computation. I mean, it is not even clear why it seems interesting for a streaming algorithms, but it is. This should be taught as a part of algorithm course. This has nothing to do with slay so much. Okay, so let us negate them first. Okay, so if I negate them, what do I get if I negate them? So first let us divide each of these guys with eta, okay. So what will we get? Dividing by 1 over eta, what will I get?
Dividing by eta.
Huh?
Are you multiplying by eta?
Yeah, so divide by eta, both sides, this is fine, right. Ln n by eta minus t equal to 1 to t p of t, this is fine, right, greater than equal to, why did I do it? So summation greater than equal to 0 m of t, you understand what it means, no, mit, okay, ln 1 minus eta whole divided by eta minus summation less than 0 mit ln 1 plus eta by eta. Okay, so now let us do one thing, let us multiply this with minus, okay, negate. So if I negate, what will I get? And why do I am negating? Because last time also I negated, if you recall correctly, because we need these things should be greater than MTPT, right. So this is why I am negating, okay. So if I negate, what do I get? Summation t equal to 1 to t MTPT, huh?
At most, you can take
Less than equal to, I want to move this side, so ln n by eta, right, right. Let us see if you people agree to this, ln n by eta plus 1 over eta summation greater than equal to 0 mi of t ln 1 minus eta am I doing something correct? I multiplied with minus sign, no? Huh?
So there should be a minus for what you wrote now. That quantity
On the
is a
right
minus.
This should be minus, no? And this should be plus, right? Right? Okay. I will take plus and move minus here, which is equal to ln n by eta plus 1 over eta summation greater than equal to 0 mi of t ln n 1 by 1 minus eta. Correct? पास किया है 10th. Look, generally I don't do all this. None of my business to do all this. I just hardly understand these equations. Okay? Okay. Now this is less than equal to ln n by eta plus 1 over eta. Now I want to substitute all those, the Taylor series and all those kind of things, just to get rid of things. Okay? So here I will greater than equal to 0 mi t. If you write down this Taylor series or something, we can replace it with eta plus eta square. This is at least this much, or think of this as a minus ln 1 minus eta. I just told you in the beginning, right? This is nothing but minus ln 1 minus eta, and I replace this with this. So why can I replace now? Okay. Okay, so this is correct. Plus 1 over eta summation less than equal to 0 mi of t. This is ln 1 plus eta, and this you can upper bound by eta minus eta square. Right? You can again you write down this will be plus minus because this is ln 1 plus eta. So it will be plus minus, but you can truncate this and prove that this is upper bounded on this because of otherwise, like because eta is again less than half, so those quantities will converge to something very small number quantity. So, okay. Okay. Now, so what happens because of all this?
You just remove 1 by eta to make it 1 plus eta inside bracket.
What should I do, Fahad? Okay, let's write down ln n by eta. At least eta can come out and get rid of this quantity. Am I right? So summation greater than equal to 0 mi of t 1 plus eta. Agreed? Similarly here I can write down one minus eta. Right? Is this correct? Is this correct? But notice one thing. Now let's open this up. Open this parent what do you call box. Ln n eta plus if I choose this term and then choose this term from the first, I can write down this is I going from 1 to t. T going from 1 to t mit. Agreed? This term and this term. Okay? Okay. And what is left for us from here is eta time greater than equal to 0 mi of t minus eta times less than 0 mi of t. Agreed?
You can remove that term, right?
What, Fahad?
The last term you can remove, right?
I don't know, Fahad.
Minus eta. Oh no, because it's a minus. It could be minus.
It could be minus, no, Fahad. Wait.
That's why they put modulus.
So this term we got already, no, Fahad?
This and the
This term and this term we got.
yeah,
Now we need, from here, somehow we need to get this, right? But that's okay.
yeah. If MIT is less than 0,
Yeah.
then it is mod with plus.
Plus, and that's it, right? So this is actually equal to ln n times eta plus summation t equal to 1 to t mi of t plus take eta. What is this? This is negative. So if I put mod minus this and then mod, then it becomes plus here, right? And anyway these are plus. So this is summation. Yay! Yes. Okay. So the two inequality which we used is here. So what did we use? We used ln 1 minus eta, okay, or minus ln 1 minus eta is less than equal to eta plus eta square. This is one thing we used. Let me use different pen. I have, what is the point? Okay. So this is used here. And what else did we use? We used that ln 1 plus eta less than or greater than equal to. No. This, is it greater than equal to or less than equal to?
There's an alternate plus and minus, right?
Hmm.
So the first two terms you take.
Wait, what happens? These are negative numbers. So MIT here is negative numbers.
And hence you need a lower bound.
Hence you need a lower bound, no? Otherwise I cannot replace this.
That's why the first two terms.
Yes. Look, this is negative term, right? So we need a lower bound. We don't need an upper bound. You don't get my point? Okay. Here, this is negative. So we need lower bound on this quantity. Okay. And then this is greater than equal to eta minus eta square. Look, I cannot replace this with some number, right? Something smaller only than 1. Okay, good. So finally we got here. So this is what is called multiplicative weight algorithm. Now notice something funny here. Okay, so can I rub this part? The whole proof is here actually. Okay. Let me write down a very beautiful corollary out of this. Okay. Okay. So this is my corollary, and I will tell you why it is a corollary, and then we will stop for today because I don't think I can give you applications of this, like set cover algorithm and this algorithm, like approximation, which is not obvious. Okay. Okay. So multiplicative weight algorithm guarantees. What is it guarantees? That after t rounds, okay, after t rounds, for any distribution, right, for any distribution P, okay, for any distribution P on the experts, okay, what happens? We get the same equality for any distribution P. Again, after T rounds for any distribution P on the experts, summation over T equal to 1 to T MT dot PT is less than equal to summation over okay, I can take this inside, right.
What is this initial distribution on exports?
Hmm?
What is this initial distribution on exports?
Hmm. Let me just 1 second file. So what he says dot P plus ln n by rho, okay. So what happens here, Fahad, is something to note. Do you understand what is happening here?
What is this P? Initial distribution. Initially, we started with the uniform distribution. The algorithm you explained,
Yes.
right? Because everything is one.
Yes.
Now you are saying you can assume P, which is any distribution, and you put initially some weights on them.
Yes.
But in the initial one, if I substitute P is equal to 1 by n, should I get that? No. Right?
Why not? If you sum them up, why not?
P equal to 1 by n, right?
Yes.
No, it's not P. Is it P equal to 1 by n?
Yes.
Then do we get that?
Look, Fahad.
Oh, yes.
Look, Fahad. What is P of t? P of t is a probability with respect to, don't think of this as a weight. Like, what is my weight? So, what was my weight of I? Weight of I in the beginning was 1, right?
Which means 1 by n
Which means 1 by n
probability.
probability, okay? So, now what is my weight? Say 1 by P of I. This is the weight I start from, right? Suppose that this is the weight I start from. The first time I definitely have this, okay. Or the other way around, other way to think is, I think the more easier way to think is as far, I'll tell you in a minute. I think, look at this, okay, look at each PI. Look, this is with respect to one particular expert, okay, right? So let's sum this up.
Okay.
Let's sum this up. Okay, let's sum this up for all experts. So what are we going to get? We are going to get n times left hand side is equal to,
Now you have a summation over 1 to n.
right, but you have also n here, right. So like, but now you have summation over each mi, right, for all I. So I am summing for all I, sum this up, because this is true with respect to each I, right. So I shall sum this up, but I use different j, okay. So it's like a double summation. So like, think of this as summation going from j equal to 1 to n and then right hand side. This is correct?
Now you divide by n.
Okay. Now, no, you will not get that far, okay. But the point is, this is less than equal to sum of these probabilities, right? Because what I mean by this is that, okay, how to say this? Okay, this is, look, it's like a convex combination of these PIs, right? It's like convex combination of all the inequality with distribution PI. Let's try to understand, right? I want to take a convex combination. What happens if we multiply now? Do you get what I'm saying? No. See, if I had all distribution 1 by root n, 1 by n, the beginning distribution, this is what we assumed, right? Then what happens? If I do all this, right, then I have 1 here,
Actually, in that quantity you wrote, if you take out that n to the right hand side,
huh,
then that 1 by n will become the product you made.
exactly,
Okay?
right,
That will happen.
that will happen, okay,
So,
excellent.
To uniform it is like, okay, for P uniform that is same. Or like it derives from there.
Yes.
Because here you wrote MT is a vector.
Okay, let's don't do this. Let's look at P, okay, P1 times left hand side plus P2 times left hand side dot 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 Pn times left hand side is equal to left hand side.
Yeah.
Agreed?
Okay.
Okay?
Now for the
Because look, this is linear combination, because if I take LHS common, summation of Pi is equal to 1. Now LHS is less than equal to P1 times LHS is equal to the first in constraint, P2 times second constraint, P3 times third constraints, and dot 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 Pn times the nth constraint, and that's what the right hand side is. Right now you don't have n and all those kind of things because this term. Okay, so this is exactly what is happening. Now it's corollary. So basically, it's a convex combination of linear combinations. Okay. Okay, good. So you could have also started with all this. Okay. So here, costs, we use cost for what purposes? To like, we say that, oh, experts are making bad choices and hence it is bad to do, but sometimes you might like to give them gains because some algorithm it might be better that costs are like gains rather than losses. Okay, right? So that MT specifies gains for each experts rather than losses. So now what you want to get as much total expected payoff as possible. Look, beforehand I wanted to minimize my total expected payoff cost, right? Because I wanted to minimize the cost, but now I wanted to maximize this. So what you do? You just use minus m of t. Look, for up until now in this algorithm we wanted to minimize the cost. Suppose I want to maximize the cost. So what should I do? You just run the loss vector, like the loss where we are doing m of t, you do it with minus m of t, and that's fine. Then you will get that you will get at least as good as this minus something, right? So what will you get is like at least this much, this minus this. Okay. Okay, so this is another corollary. What is a corollary? And we are assuming this. Suppose we want multiplicative weight algorithm for gains. Then after t rounds, for every expert I, what is this? We have summation t going from 1 to t, m of t, p of t is at least, right, as much as this, mi of t, t going from 1 to t minus this quantity, summation t going from 1 to t mi of t minus ln n by tau, right. So whatever solution you are giving is as good, like it is very, like it is as good as the best experts if you have followed the best experts advice, right. And how do you prove? Simply use minus MIT in the proof, right. So you are saying, oh, I will gain this much, right. Now I say, okay, fine. So in the other direction I just do minus, so that now that becomes, look, if you want, look, if I do minus, then the previous algorithm minimizes, it means you are maximizing here, right, and that's it, right. Look, what was the previous algorithm? It was trying to minimize the cost, and I want to maximize my cost, so I just negate my cost and say, hey, with respect to this, if you minimize, you have maximized with respect to my original cost. So if I run the old algorithm but with cost vector minus mi over, like whatever you give me the cost, I take negate and I run the same algorithm, then I can prove this bound, and because of this minus, you don't have to multiply like minus, so everything will go other side and you will get this. Because of minus, you don't have to multiply with minus or something because this inequality will give. Okay,